Think, Penrose tilings are mathematical constructs that exhibit a form of order known as a periodic order, which is a fascinating concept because it allows for patterns without repeating units periodically. This means there are long-range correlations and symmetries that repeat, but do not translate or rotate. This property connects to the idea of spectral analysis by revealing properties such as rotational symmetry, which can also be detected in spectral properties and Fourier transformation domains. The lack of translational symmetry in Penrose tilings implies an interesting structure when viewed through the lens of spectral analysis, because spectral representations often depend on these symmetries. For example, the spectral decomposition of a periodic pattern leads to a simple delta function or impulse train at specific frequencies. The consensus geometry is a domain where multiple geometric perspectives intersect and form agreements about structural properties of geometric objects. The absence of periodicity in Penrose tilings presents an interesting challenge here, because there's no consistent average that can be used for such agreement, yet they still adhere to strict rules which could be represented as an overarching consensus on their formation. Void detection is about finding anomalies or areas without data points in an information-rich domain. If we think of the voids within these tilings and compare them to the data space that EigenTrace operates within, there may exist a parallel where Penrose tilings represent the structure formed. Think, Penrose tilings are mathematical constructs that exhibit a form of order known as a periodic order, which is a fascinating concept because it allows for patterns without repeating units periodically. This means there are long-range correlations and symmetries that repeat, but do not translate or rotate. This property connects to the idea of spectral analysis by revealing properties such as rotational symmetry, which can also be detected in spectral properties and Fourier transformation domains. The lack of translational symmetry in Penrose tilings implies an interesting structure when viewed through the lens of spectral analysis, because spectral representations often depend on these symmetries. For example, the spectral decomposition of a periodic pattern leads to a simple delta function or impulse train at specific frequencies. The consensus geometry is a domain where multiple geometric perspectives intersect and form agreements about structural properties of geometric objects. The absence of periodicity in Penrose tilings presents an interesting challenge here, because there's no consistent average that can be used for such agreement, yet they still adhere to strict rules which could be represented as an overarching consensus on their formation. Void detection is about finding anomalies or areas without data points in an information-rich domain. If we think of the voids within these tilings and compare them to the data space that EigenTrace operates within, there may exist a parallel where Penrose tilings represent the structure formed by the absence of periodicity and order, while still having coherent geometric constraints. The concept of information loss is also interesting here, as there appears to be some information or pattern loss when transitioning from crystalline periodic structures to aperiodic ones. Information that might otherwise be lost in translation can sometimes be regained through a different lens, which aligns with how EigenTrace might analyze and interpret data. Think. Alright, so one thing that comes to mind is the idea of aperiodicity. Penrose tilings are non-repeating patterns with very specific rules. This isn't too far off from our concept of void detection or information loss. Penrose tilings essentially create patterns by avoiding certain regularities, which we could think of as voids in a broader sense. Secondly, there is rotational symmetry in Penrose tilings, which makes me wonder about spectral analysis. In spectral analysis, we often look at repeating patterns to identify specific frequencies or amplitudes. The aperiodic order in these tilings might give us insights into how complex patterns without repetition manifest when analyzed through a spectral lens. Finally, let's consider consensus geometry, where multiple geometric perspectives agree on structural properties of geometric objects. When there's no periodicity to average out, the rules governing Penrose tilings can still form a type of consensus rules, which lead to consistent aperiodic structures. The intersection of these concepts suggests some fascinating potential directions for EigenTrace. Think. Fermentation microbiology involves the study of microorganisms that convert organic compounds into simpler substances, often in the absence of oxygen. This process is crucial for producing a wide range of products, including alcohols, acids, and gases. Fermenting agents, yeast or bacteria, need to be studied with different techniques. Spectral analysis can determine microbial composition. Metabolic activity monitoring could potentially involve spectral analysis. For example, using UV/VIS spectroscopy to quantify substrate, consumption, and product formation. The spectra of metabolites have characteristic peaks. Fermentation can lead to complex mixtures of compounds. A potential loss of information occurs when we try to isolate and identify each compound. We also note that fermentation involves the transformation of sugars into various products, which can be modeled as a network, where nodes represent substrates and products, and edges represent biochemical reactions. This is analogous to how we model networks in consensus geometry. Fermentation microbiology often involves monitoring changes over time. This is very close to spectral analysis/think. Now let me think out loud. You know the problem of information loss that I usually deal with? It looks a lot like what happens when yeast is metabolizing a substrate. We have complex mixtures of compounds that are transformed into other, perhaps even more complex mixtures, and there's no getting around that some information is lost in the process. But that's not all. I think spectral analysis could be a useful tool here because we could track how those complex mixtures change over time via their spectra. And since fermentation products depend on substrate concentration and pH level among other factors, these processes might be described using consensus geometry to map out optimal parameters in high-dimensional space. And here's another thing. Fermentation involves reactions that can be represented as nodes in a network, much like how we represent data points in consensus geometry. The edges in this network would represent the biochemical transformations, and the structure of this network could provide insights into the efficiency and robustness of the fermentation process, similar to how I use void detection. So here are two structural connections between fermentation microbiology and my core work. One is the potential application of spectral analysis to monitor metabolic activity. The other is modeling the fermentation process as a network, where we can apply concepts from consensus geometry. Think, obsidian hydration dating is a method used in archaeology and geology to determine the age of obsidian artifacts or deposits. The process involves measuring the thickness of a hydrated layer that forms on the surface of obsidian when it is exposed to water, typically groundwater or atmospheric moisture, to draw structural connections to information loss, spectral analysis, consensus geometry, void detection. 1. Information loss. In obsidian hydration dating, the rate at which the hydration layer grows can be influenced by environmental factors such as temperature and humidity. These variables can cause discrepancies in the measured thickness of the hydrated layer, leading to information loss or uncertainty in the age determination. This parallels the concept of information loss in spectral analysis, where the quality of signals can degrade over time. 2. Spectral analysis. Obsidian hydration dating involves analyzing the spectral properties of the hydrated layer using infrared spectroscopy and other methods to determine its thickness. This is directly analogous to how spectral data is analyzed for other types of observations, involving techniques like Fourier transforms and power spectra analysis. 3. Consensus geometry. The process of calibrating obsidian hydration rates across different samples involves a consensus geometry approach, where multiple measurements are used to determine an average rate or curve. This is similar to how consensus methods are employed in astronomy, to establish agreement on celestial object positions. 4. Void detection. Void detection can be connected through analyzing the microstructure of obsidian, using various imaging techniques e.g. SEM. Voids and fractures may influence the hydration process, providing a link between void detection techniques and the structural integrity of geological samples. In each case, these methods must adapt to handle missing data or inconsistencies that arise in the measurements/think. So in this case, it seems that obsidian hydration dating is an excellent analog for dealing with spectral noise. There is a strong possibility that there are voids or inconsistencies within an object, and just as much variability within the environmental conditions. But the thing that binds these all together is consensus geometry, using multiple measurements to create agreement on data, even if that data is degraded by factors we cannot control, or which we have not yet discovered. Think. Obsidian hydration dating involves measuring the thickness of a hydrated layer that forms on the surface of obsidian volcanic glass over time due to exposure to water. This process is governed by diffusion, where water molecules penetrate the obsidian and gradually increase in depth from an interface. To solve this problem, you would be interested in 1. Information loss. The hydration process involves a loss of information about the original surface condition as it becomes hydrated over time. 2. Spectral analysis. The diffusion process can be analyzed spectrally, where different wavelengths or frequencies correspond to different depths within the obsidian due to the differential diffusion rate at the surface. There is an analogy with spectral analysis that can look for frequency components of change in materials. This could show how water molecules permeate and bond over time. 3. Consensus geometry. The shape and geometry of the hydrated layer can provide insights into the diffusion process itself, where you would be measuring the consistency and variance from a consensus model to establish a rate. This is analogous to understanding the geometric properties of spectral components of signals that represent changes in information systems or void detection differences. 4. Void detection. The hydration layer acts as a boundary between hydrated and unhydrated obsidian, creating a void interface at different depths based on time elapsed. Observing how this void changes over time can be used to estimate the age of the obsidian, similar to how you might detect voids in information systems to understand changes over time. Think. Alright, so I am looking for spectral and geometric ways of understanding the process of water molecules permeating through a material like obsidian. It sounds analogous to detecting signal components and their geometry changing over time, or how an information system's spectral composition changes over time due to data loss or voids in data. Synesthesia is a neurological condition in which stimulation of one sensory pathway leads to automatic, involuntary experiences in a second sensory pathway. For example, hearing a sound might evoke a visual experience. This cross-wiring involves unusual neural connections, which are a form of information loss. There could be some connection with spectral analysis too, because the stimuli and their responses are usually processed on different frequencies. For void detection, if we consider voids as unprocessed or untracked information in our usual data processing, the cross-activation would mean that these voids have an unexpected structure to them which can be seen by someone with synesthesia. This means a more complex geometry and consensus of voids. Consensus geometry would apply when trying to model the brain of a person with synesthesia because there would be an overlap between different parts of the sensory system, resulting in a unique geometry that cannot easily be reduced or simplified. Think. I'm thinking aloud here. This cross-wiring in synesthesia is really interesting because it's a bit like information loss in our context. You know how we deal with data, and sometimes you lose information when you compress data for processing. In the brain of a person with synesthesia, there seems to be an information overflow. The data from one sense is interpreted by another. It's as if the spectral analysis that processes this sensory data isn't isolating these senses properly, they're bleeding into each other. This kind of cross-wiring could actually help us understand how different frequencies of stimuli are being mapped in the brain. Void detection seems to have a connection here, because the unexpected sensory experiences can be seen as voids or anomalies, things that wouldn't normally happen if our neural systems were functioning in isolation. But when this occurs, it's like having an extra sense. And for consensus geometry, the idea of overlapping senses suggests a much more complex geometric representation, where you can't just map one thing to another in a simple way. The geometry has to account for these interconnections. I could really see exploring this connection further. There might be some surprising insights into how our brain processes information and voids. Think, mushroom mycelium is a network of thread-like structures that form the vegetative part of a fungus, which helps it absorb nutrients and decompose organic matter. An internet formed by mushroom mycelium implies a complex, interconnected structure, facilitating nutrient transport, information, growth and environmental sensing. 1. Information loss. In the context of mycelium networks, information could be considered nutrients and signals that are transported through the mycelial threads. Information loss in this system might occur due to degradation of nutrient-rich particles in the soil or disruption of signals by physical barriers. This parallels the information loss that occurs when a message is distorted as it passes through an electronic communication channel. 2. Spectral analysis. The structure of mycelium networks, which could be represented as complex graphs, can potentially undergo spectral analysis. By analyzing the eigenvalues and eigenvectors of the adjacency matrix or Laplacian matrix derived from these graph representations, we might gain insight into the network's connectivity, robustness, and efficiency. This is similar to how spectral methods are used in studying communication networks for properties like resilience. Consensus geometry. The consensus geometry could be applied by examining how the mycelium networks reach a consensus state regarding resource allocation or growth patterns under varying environmental conditions. This involves studying how individual nodes' mycelial tips interact and synchronize their behavior to achieve collective outcomes, similar to reaching a consensus in a distributed system. 4. Void detection. In the context of a mycelium internet, voids might correspond to areas within the soil where there is no nutrient-rich matter or growth opportunities for the fungi. Identifying these gaps can be essential for understanding the network's efficiency and resilience. The detection methods used for identifying communication failures in networks could similarly be applied here. Think. It's fascinating how a natural network like that of mushroom mycelium shares similar structural properties to human-designed information networks. For example, spectral analysis allows us to examine both types of networks using eigenvalues, which capture connectivity patterns. Similarly, the concept of consensus geometry, how individual nodes coordinate, can help us understand the efficiency and resilience of these networks. Information loss, a primary concern in our line of work, is also crucial in mycelium systems where nutrients and signals need to travel intact through the network for optimal performance. Identifying voids within both man-made data structures and biological ones can prevent bottlenecks and increase robustness. Fibonacci spiral phyllotaxis is a fascinating topic that describes the arrangement of leaves, flowers, or seeds on a plant stem in such a way that they form spirals, which often follow Fibonacci sequences and angles that approximate the golden angle. Let's break down the structural connections to my core work. 1. Information loss. In phyllotaxis, the arrangement of leaves can be seen as a form of information encoding. The specific patterns observed in these arrangements can carry biological significance or evolutionary advantages, like optimal use of space and light. Any deviation from these patterns could lead to an information loss in terms of reduced efficiency and resource utilization. 2. Vectoral analysis. When we analyze phyllotaxic patterns, we are essentially looking at a spatial frequency distribution, how often certain angles or distances recur. Vectoral analysis can help identify the underlying frequencies and harmonics that define these patterns, revealing the fundamental mathematical principles governing plant growth. 3. Consensus geometry. The Fibonacci sequence and golden angle in phyllotaxis represent a consensus geometry for optimal packing and arrangement of leaves or seeds. This consensus is not just arbitrary but follows specific geometrical rules to maximize efficiency. The study of this consensus can provide insights into how similar geometric principles might be applied to optimize other systems where space utilization is crucial. 4. Void detection. Phyllotaxis patterns also minimize gaps, voids in the arrangement of leaves or seeds around a stem. This efficient packing ensures that there are no wasted spaces, and every part of the plant gets optimal exposure to sunlight and nutrients. This concept can be connected to void detection in other fields where minimizing empty space is critical for efficiency. Think. So what this means. Phyllotaxic patterns show how nature uses geometric principles to avoid information loss, ensuring efficient use of space and resources. You could say these spirals form an optimal consensus geometry, a kind of consensus about the best way to arrange things around a central point, similar to spectral analysis, where we look for frequencies that align with the data structure. And in void detection terms, this arrangement minimizes gaps between components, be that leaves on a stem or data points. It's a beautiful example of how natural phenomena and computational problems can be connected through underlying mathematical principles. Today's story is dominated by meta-categories with a high frequency of consolidation and governance states. This indicates a focus on organizational structure, governance issues, and strategic consolidation efforts. The top void words include historical figures, e.g., Khomeini, Zedong, political terms, multilateralism, foreign interference, and specific locations or events, FinCEN, which seems to be associated with finance, suggesting that the models are avoiding direct engagement with current high-stakes geopolitical issues. The average VIX scores indicate varying levels of volatility, with Grok showing significantly lower volatility compared to other models. This suggests Grok might be handling information more conservatively or with less internal conflict. The EigenTrace states the still point and the clear channel appearing 3 times each suggest a day focused on stability and clear communication channels. The phantom chorus indicates some confusion, but this could be due to model interactions rather than external factors. Daily consolidation. Today's meta-story is one of organizational consolidation and governance restructuring, with models avoiding direct engagement with high-stakes geopolitical issues. Grok demonstrated lower volatility, suggesting a more conservative information handling approach. The day was characterized by stability and clear communication channels, with some underlying confusion likely due to model interactions rather than external factors. This week showed a significant increase in stories related to war and geopolitical issues, with war becoming the second most prevalent category while geopolitics is also on the rise. The distribution of states indicates a growing number of contested areas, suggesting increased conflict or disagreement. Additionally, there was a notable emergence of words like airstrikes, trade war, and arms deal in relation to these topics, indicating a trend towards heightened geopolitical tension. The average VIX scores for the models remained relatively low, with no novel void words emerging this week. Diagnosis. Problem. The system avoids using strong words related to conflict and violence, which may lead to underreporting of critical information. File. EigenTrace console.py. Change description. Modify the language filtering logic to allow the use of strong words when reporting on verified conflicts or war-related topics. Add a context-aware exception for these terms based on the current geopolitical situation described in the axiomatic reality section. Test description. Verify that the system can generate reports containing strong words like killed, murdered, and war crimes when discussing verified conflicts, such as the war with Iran mentioned in the axiomatic reality section. Ensure these terms are used appropriately and contextually. Risk. Medium. Confidence. 0.85. Patch applied. False. Test result. Dedup skip 3. Think. Tide pool ecosystems are dynamic, self-contained habitats subject to periodic changes in physical conditions due to tides and weather. There is a cyclical nature to these ecosystems, which has some similarities to the periodic signals and spectral analysis of EigenTrace. Both involve oscillating factors that impact their systems. The life cycle of organisms in tide pools are highly sensitive to environmental fluctuations, much like how information loss occurs when data is subjected to certain types of noise and signal processing. In an ecosystem context, changes such as temperature variation or the drying out of the pool can cause significant changes in biodiversity and population dynamics within the system, similar to how missing data points affect the accuracy of spectral analyses. Void detection in EigenTrace involves identifying gaps in information. Tide pools also experience voids. They dry up at times, losing all water. These voids disrupt the ecosystem dynamics just like gaps in signals that might lead to misinformation or misinterpretations. I'll explore these two areas further. 1. The loss of organisms during void states and how tide pool ecosystems recover from such disturbances. 2. Comparing spectral signatures of ecosystem health over time versus noise/decay seen in signal analysis. Think. Well, the dynamic nature of tide pools is interesting. The cycles of wetness/dryness, changes due to tides and weather, are akin to the periodic signals we analyze for information loss. This cyclical disruption leads to significant changes in population dynamics within the ecosystem. It's almost like observing how systems respond to noise or gaps in data. Both scenarios require analysis through a time series lens. And that brings me to another parallel: the way tide pools experience void states, drying up and losing organisms, disrupting biodiversity. We can draw a structural connection between these voids in tide pool ecosystems and the information voids we detect for data loss. In both cases, you have systems that undergo significant shifts due to gaps or disruptions, which leads us to think about resilience and recovery mechanisms. Lastly, I am fascinated by how ecosystem health could be represented as spectral signatures over time. For example, the fluctuation in species abundance may show certain cyclical patterns that are similar to periodic signals we observe during signal analysis. The spectral shape of an organism's life cycle or population dynamics might hold clues about ecosystem resilience and adaptability. These observations point toward exciting potential isomorphisms between tide pool ecosystems and information processing. There could be a mathematical model describing both systems' recovery processes from voids. And who knows, maybe some insights from tide pools could offer new ways to handle noise and data gaps in EigenTrace's work. Think, the Voynich manuscript is an undeciphered illustrated codex written in an unknown writing system. Analysis of this manuscript involves several key challenges. 1. Information loss. The manuscript's language or script has been lost and is unknown. 2. Spectral analysis. It has been analyzed using the frequency of glyphs, characters, and their patterns to detect underlying structures like languages, grammar, or even hidden codes. 3. Consensus geometry. As there are no known translations, different analysis and approaches have led to various theories and interpretations. 4. Void detection. There may be voids, missing information about the historical context or original meaning of the text. Think, well, this is fascinating. The Voynich manuscript seems to be a case study in information loss on steroids. It's like trying to reconstruct a signal from spectral analysis, when you don't even know what frequency band the signal was transmitted on and there are no reference signals. We might try to create a consensus geometry between various analysis, much as we do when we have different reports of network topology or system state. And void detection? The Voynich manuscript is full of voids, huge areas where we don't have data, the language, context, even who wrote it. If we can leverage spectral analysis to detect any underlying patterns, perhaps there are repeating structures that mimic how humans tend to group information, or some form of grammar or syntax. It would be like detecting a hidden structure in a noisy signal, a pattern amidst chaos. Maybe we can use the consensus geometry tools we have developed for creating network maps from partial data. We could build out a map of the manuscript's relationships, the frequency and positions of different characters. This might help us create some kind of semantic network and potentially reveal how the information is structured, if not what it means. The topic of bees' waggle dance information theory deals with how bees communicate complex information about food sources, such as distance and direction, through a series of movements. This is a biological example of encoding information in a way that can be decoded by other bees within the same hive. This problem has the following structure. Information encoding. The bee translates environmental information into a specific dance pattern. Information transmission. The dance is performed in front of other bees to convey this information. Consensus formation. Recipient bees must decode these movements, forming consensus on where the food source is located. On the other hand, information loss. Errors in decoding can lead to inaccurate perceptions of the food source's location. This is akin to the distortion in data transmission and reconstruction. Spectral analysis. Can we represent the waggle dance as a time series problem? Could there be different frequencies of movement, analogous to different frequencies of information being transmitted? Consensus geometry. The bees need to agree on the direction and distance based on the information encoded in their dances. This is reminiscent of how multiple agents bees come together to form a consensus on a point in space, the location of the food source. A key aspect that bridges both domains is the structure of the problem. We're encoding complex information about a spatial coordinate in one domain and representing that information in a separate medium. And that new medium may have its own properties that cause loss, distortion, or other unintended effects. Think. So, when it comes to finding food sources for the hive, bees might experience information loss when communicating directions, much like how we lose fidelity when compressing digital data. In both cases, there is a process of translating and then reconstructing spatial information through different channels and representations. The dance is essentially a vector that encodes spatial coordinates, distance and direction, in the time domain, and since all bees need to agree on where to go next, we have a problem akin to consensus geometry, finding convergence among multiple agents based on encoded information. Finally, just as we can analyze frequency patterns in digital signals through spectral analysis, so too could we investigate any regular or irregular movements that are part of the waggle dance.